Now it's time for the fun, or the most interesting part of it, I think. We're going to talk about voltaic or galvanic cells. I will typically call them voltaic cells, and voltaic cells are a type of battery and primitive, but it shows the principles of how basically all batteries work, if not all batteries. Voltaic cells are batteries that use a spontaneous reaction to do work by separating the oxidation and reduction half reactions in space. And that will mean that the electrons are forced through a wire and can light up a light bulb. So here's the voltaic cell that we're going to talk about first. And I'm going to draw what a voltaic cell looks like always. So it always has, let's see, that should be good. Always has two beakers, and each of these beakers has a solution. And these two beakers are connected by what's called a salt bridge. And inside the salt bridge is going to be ions. And let's suppose that the salt bridge is filled with sodium chloride saturated. And saturated just means as many ions as possible. And let's suppose, so it's sodium chloride, so it's going to be, so Na plus Cl minus, Na plus Cl minus, all the way through the salt bridge. So Na plus Cl minus, Na plus, Na plus Cl minus, dot, dot, dot. So the entire salt bridge is packed with as many ions as possible. And then there's two electrodes, and electrodes are commonly pieces of metal, but we'll also see that graphite is a good electrode. So, and then these two, and I sort of ran out of space, so I'll put it up here. Are connected to a light bulb, like so. It doesn't always have to be like this, but typically I'm going to put the oxidation half reaction on the left, certainly when I draw them, and I'm going to put the reduction half reaction on the right. Whenever solving problems in my class, though, please be aware that I could have switched these, but whenever I do my own drawing, this is how it'll be. And let's see, I think this is pretty much the same for every single voltaic cell that we're going to draw. Then we can start personalizing it for the reaction that we've got here. So we have zinc solid going to zinc 2 plus aqueous. That means this is going to be our oxidation half reaction. And so that means our electrode here is going to be made out of zinc. And we're going to have zinc 2 plus ions in solution. And that doesn't mean that's the only thing that's there, but that's the only thing that we would show that comes in the net ionic equation for this process. Anytime you have a positive ion, it's always a good idea to at least think about what the negative or counter ion would be. And so let's just put in some sulfate in there. The other ions that you can put in here that are good, you could also put chloride, which is always good, and nitrate is always good as well. Sulfate's good too. Let's see. And the oxidation half reaction is going to go like this. You have some zinc solid. It is going to give up 2 electrons to become zinc 2 plus. And so this zinc half reaction should actually have 2 electrons there as well. And the place that the oxidation occurs is called the anode. And these two electrons are then going to go through the wire, ding, light up the light bulb, and come over here to the other electrode. And the other electrode is called the cathode. And the cathode, well, our cathode process is going to take copper ions and turn them into copper solid. So we're going to need copper ions in solution. We're going to need some other negative ion in solution, and these become what are called the electrolytes, meaning that strong electrolytes. Of course, we've talked about that before too. Our half reaction for reduction is going to be copper 2 plus 2 electrons goes to copper solid. We're making copper solid, so we don't have to have any copper solid already present. We could call that copper solid. Other choices is that the cathode can always be graphite, and graphite is carbon solid, so you can just call it carbon solid, that's fine. Platinum is sometimes used, though it's a little bit expensive for what I do. And let's see, our process over here on the reduction side is that you take a copper ion from the solution, you pair it up with 2 electrons, and you make copper solid. Okay, and so let's see. That is a good picture of a voltaic cell that shows that the electrons go through here. And now I think, yeah, it's time to do, well, let's make one other node here. So, and let's do it in green. Yeah, this is important. We'll put it on this picture. This is always used. Okay, so you are creating zinc ions in the oxidation half reaction. So here we are creating Zn2+. So this beaker becomes more positive. On the other hand, over here, we've got copper 2 pluses that are reacting away. So we are reacting away copper 2 pluses. If you take away positives while leaving the negatives the same, the beaker becomes more negative. And very shortly after this process starts, this becomes too positive, so electrons do not want to leave anymore. And this becomes too negative, so electrons don't want to go in it anymore. And so now it's time we talk about the salt bridge. The salt bridge is effectively an ion line, an ion bridge, such that so if once you have a buildup of charge here, a positive ion we'll get there in just a minute. There we go. Sorry about that. Get over there. There we go. a positive ion, zinc, can go in here and push a positive sodium ion out the other side. Blink. And so every time two electrons go through the wire, a zinc ion has to go in here to maintain charge balance. And every time, and knocking out two of these sodiums, and every time a copper reacts away here, a sulfate has to go in and kick out an equivalent amount of charge on the other side. So the salt bridge allows ion movement to maintain charge balance. Allows ion movement to maintain charge balance. In fact, the electrons can then only move as fast as the ions can move, because ions are much slower and clunkier than electrons. Electrons are much lighter. In fact, the electrons go through the wire. The ions, and maybe this is obvious, but they're too big to go through the wire, so they can only go through the salt bridge. But you can only generate as much electron movement as you can ion movement in here. So it's not a great battery, but it's a great way to visualize how batteries work, and it's relatively straightforward to make in a chemistry lab as well. And it can light up a light bulb if you get a small enough light bulb. Okay. All right, so that's our full picture. Now let's do some notes on the next page. And so we'll take notes and we'll refer to our picture. So notes on the Voltaic cell. Let's do these in blue. Start in blue anyway. 1, this is a spontaneous reaction. And when we hear the word spontaneous, maybe what we think is that delta G, the change in free energy for the reaction, is less than 0. That's awesome. It will turn out that what we call E, which is our symbol for the voltage, will be greater than 0. And if the reaction is spontaneous, it means QC is less than KC. And therefore, all three of these things and all three of the sets of information we've talked about them are really talking about different ways of looking at how to tell when a reaction is spontaneous. Okay. Let's see. So over time, the zinc solid anode will react away. So if you allow this reaction to go long enough, there will be no zinc left. Over time, copper solid deposits on the cathode. Whatever that cathode is, we said that the cathode could be copper itself, and that's fine. You're just adding more copper. It could also be graphite, which is carbon solid. It could be platinum as well. And a major issue in batteries is, well, this kind of battery, once the zinc leaves, you can't get it to come back. But a major issue in batteries is when the oxidation reduction occurs, how do you keep the oxidized version around so that you can recharge the battery in theory, because this would not be a rechargeable battery. It actually could be pretty rechargeable on this side, because you could, if you reverse this process, take the copper and kick it back out into the solution. Okay. So for one way to make the ion, so what I said before is only as many electrons can move as ions move, and since ions move more slowly, the electrons move pretty slowly in this process. So my note is going to say, to allow the ions to move faster, use a porous cup. And a porous cup is basically like a potted plant cup, if you've ever used those. It's sort of unfinished ceramic. Which is dried clay. And if you've ever noticed, it will appear to have little holes in it. And if you were to do a picture of a voltaic cell in a porous cup, it would look something like this. Here's a beaker. Inside it is another beaker, is the porous cup. And let's assume that they're pretty close to the same levels of solution. Let me get that on screen there. And what you would do is you'd put one of the electrodes in the solution, one in the beaker, one in the porous cup. You'd connect them to a light bulb. And here I have mixed up because, well, it doesn't actually matter which one you do. Let's have this one be the zinc and this one be the copper. And then we put zinc and sulfate in the solution. We'd have copper and sulfate here. And it turns out that the ions can flow much more freely through the porous cup than they can through the salt bridge. There's less distance to travel for one, there's more surface area, and so here it's just a faster way to do it. And so sometimes you'll see that should you get into the lab and get to do that. So porous cup is just a faster way to do it, has more surface area. And so surface area would be all this surface area of the porous cup. So this is the porous cup. And this is a beaker for the other solution. Anyway, so just a note, if you ever see a voltaic cell in the lab. Let's see. I think that's all of my notes for now. Yep. So I think we have a couple other notes here, and we also have a video. So let's watch the video.
In a voltaic electrochemical cell, an oxidation occurs at an electrode called the anode. The electrons released at the anode travel through a wire to another electrode called the cathode, where the electrons are consumed in a reduction reaction. Anions are then shuttled through a salt bridge from the cathode compartment to the anode compartment. Otherwise, a net negative charge would build up in the cathode compartment. The negative charges move in a circuit through the cell.
And here we go for our second video. And that one's not as amazing, but what it shows is that when it's connected, there is a voltage here, and when it's disconnected, there is no voltage, showing the difference. And this is actually copper metal with copper sulfate solution, and then it looks like that's very likely zinc with zinc sulfate solution as well. And now I'm trying to think if I have any other notes. I think that's it for the notes, so we'll leave it there.